So hello everybody, welcome to this first seminar for 2023. So today we have a pleasure to welcome Elvey Price. Elvey Price did his PhD in Melbourne with Tony Gutman, and then he moved for a postdoc in Bordeaux, and now he has a CNRS position in Tours. And today he will talk about counting lattice rows by winding angle.
Thank you. So thanks everyone for coming, and thanks for the invitation to give the presentation. So yeah, so I'm going to be talking about this enumeration problem where we count lattice rows by winding angle. So just as an introduction to sort of the world of enumerative combinatorics, which is the world in which I work. So in general, for questions in enumerative combinatorics, we consider objects of some form which have some notion of size. And so in general, we want to count the number of objects an of size n for each n, or equivalently to determine the generating function at, which is defined as the sum of an times t to the n, or n. Okay, so ideally for any question of this form, we'd like to find an exact solution. So that is to determine the value an exactly, or the generating function exactly. But so I've sort of drawn a picture of different aims that are important for us. So another aim is to determine the asymptotics, so that is the large n behavior of the values an, and so that's particularly the side of enumerative combinatorics which is generally the most interesting part for people in probability and physics. And we also consider it's also nice to be able to compute the exact values of an for small n. And so something which is particularly relevant to my work is functional equations. So functional equations are a tool that we use to get all of these other three things. Okay, so just to start with a simple example, if we want to count walks walks of n steps on the square lattice, so then we can define the generating function w of t to be the sum of wn times t to the n, which starts like this. And so if we want to I think maybe the battery has run out or something. Unless I just pressed the off button somewhere.
I will.
Okay, thanks. Sure. Okay, so yeah, with this example, we want to count the number of walks of each length. So we can write a functional equation for this, which says that a walk, which is counted by w of t, is either has no steps, in which case we just get one, or it's a walk with a step added at the end, in which case there are 4 options for the step we add, and we also have to multiply by t because we're increasing the length by 1, and t is counting the length. And so we end up with 4t times w of t. We can solve this exactly by dividing by the factor of wt, and it has this simple asymptotic form. Yep.
Functional equations usually come from the recursion, right? Or are there other ways?
Yeah, exactly. So a functional equation is sort of a way of rewriting the recursion. It's essentially you can say a functional equation is a recursive equation. It's just that well, we'll see that it's so for this example, you could just of course use a recursion or just the logic that for each step there are 4 choices, so for a walk of length n there are 4 to the n choices. But we'll see that it's useful, it's often useful to consider functional equations rather than recursion.
Sorry.
Yeah.
Do you have an interpretation for the simple pole and its residue?
Yeah, so the simple the fact that there's a simple pole at t equals 1 on 4 is related to the fact that it has this asymptotic form 4 to the n. So if there was a double pole, for example, it would be n times 4 to the n. So is this a question of the... Right, so I mean, so there's a relation between the fact that it has a simple pole and the asymptotics. Yeah, I guess there's some sort of physical interpretation as well.
Can continue.
Okay. Okay, so that was a univariate version. So if we so often we want to consider. Okay, so
This one is a
this, but,
function laser.
okay, but I guess I should still use the pointer for people online.
Yes.
Oh, I might forget sometimes, unless it's this. No, it's just a laser. Okay, anyway, so.
I guess the simple pole is because it doesn't have any memory.
Right.
So
Yeah,
if you
yeah.
had a more complicated denominator, you would have some subleading terms which come from the memory.
Sure. Yep. Yep. So it's 3 and something. Okay, so so that was the univariate version, which is sort of the simplest version. But in general, we'll be interested in questions with more variables. Okay, so here we let Wij(n) be the number of walks with n steps, which start at 0, 0 and end at ij. So now we're including the information about the endpoint of the walk. And so then we can write a generating function, which is the sum of Wij(n), where we now have x to the power of I, y to the j, and t to the n. So x counting the final x coordinate, y with the information of the final y coordinate, and t still counting the length. Okay, so again, we can get a functional equation. Here we, so again, for walks of 0 length, we just get 1. And then for all other walks, we can think of them as a walk with a step added at the end. So, so for walks with an up step added at the end, we get a yt factor from the up step. So we get yt times w. If we have a right step at the end, we get xt times w, and so on. And so in the end, we get this functional equation. The pictures aren't part of the functional equation, they're just for describing where the terms come from. And again, we have an exact solution where we just divide by the factor of w. Okay, so now we're still interested in asymptotics, but there are sort of lots of questions that we could ask about asymptotics because we now have more information. So just as one example of an asymptotic question we can get from this, if we now count excursions, so walk starting and ending at the same point, then we get, well, we have this exact form, which has this asymptotic growth rate. Okay, and yeah, so we could also ask questions like what's the distribution of the final coordinate of a random walk of length n, and so all that sort of information is contained in the exact solution. Okay, so just to summarize that sort of warm-up example, we wrote functional equations, or equivalently a recursion, which we solved to get an exact solution, and then we can analyze the exact solution to get asymptotic information. So we can also get the exact. We can also calculate exactly values in the sequence, so from the exact solution. So that's nice. So we basically got everything we want from these exact solutions. And so in the talk, when I describe walks by winding angle, it will follow this same path. That we'll get functional equations, which we solve exactly, and then get some asymptotic information about them. Okay, so this talk is about walks by winding angle. So it's walks where we add in one extra piece of information, which is how much the walk winds around the center point. So for example, for this case, if we have a dog doing a walk, the winding angle is how much the leash wraps around the person's legs. Okay, so right, so yeah, I'll start by introducing talking about background of walks by winding angle, and introducing the precise model that I'll be solving. So then in the second part, I'll describe the functional equations that we derive from the model. Then for the third part, I'll sort of loosely describe how we solve the functional equations. And then finally, some special cases. So the introduction. So in physics, this is used as a model for the winding of long chain polymers around some rod.
But now, is your walk self-intersecting or not?
It can, so it can self-intersect. So it's not a self-avoiding walk, but so the reason why it, so that may make a difference, but it makes less difference in higher dimension. So, so if you take a three-dimensional polymer winding around some rod, then it's almost a random walk. It wouldn't self-intersect too much anyway. And then if you take like a four-dimensional walk winding around some plane, I guess, then it's very much like a random walk. But anyway, so it's a simplified model.
It's a random walk, no? What you're doing now.
Yeah, I mean, I can't say that I produced this walk randomly, but yes. But yeah, exactly. It's random walks. The real reason why I'm studying random walks and not self-avoiding walks is because self-avoiding walks are too hard. Okay. Yeah, so for some history on this. So the, I guess, first big result was by Spitzer, who considered winding, so rather than winding of a walk, winding of Brownian motion, which if anyone doesn't know about Brownian motion, it's just essentially walks with infinitely small steps. Okay, so if you take a Brownian motion at time t in 2 dimensions, then the winding will behave like this. So we need to rescale by log t. So sort of in general, the winding will be around log t. So after we rescale, the density function in the limit will be this. Okay, but there's a bit of a physical problem with this, because most of the winding in this model happens very, very close to the point that you're winding around. And so Pittman and York considered a model where you only count the winding that happens around outside some small disk around the origin that you're winding around. And so in that case, the rescaling is the same, so we still rescale by log t, but the density has so it dies off much more quickly. So it's just this step.
What is the radius of the disk?
Yes.
So the radius doesn't matter in the limit,
Okay.
because most of the winding happens either very, very close or sort of far away in the limit.
Sorry, so your angle can be, it does not have to be between 0 and 2 pi, right? It can wind several times.
Yeah, so you can't, yeah.
But if you don't remove the disk and when you go through the origin again, how do you count the angle?
So I think it won't go through the origin, or maybe it doesn't matter in the limit. So I guess a Brownian motion is sort of, because it's in r squared, it will, the probability 0 that it will actually go through the origin. Okay.
Yeah, in 2 dimension,
Okay, good.
you will read the origin.
But yeah, so sorry, I should have clarified that for my models for walks, I'm going to say that the walk can't go through the origin. Or alternatively, you could just choose a point to wind around. Right. Okay. Sorry. So for the so Belizal proved that winding random walks have the same behavior, but in that case, you have to choose a point that's not, that you know you won't pass through. So the point that's not on the lattice, or in fact, his result had many sort of many different versions of random walks. It could be sort of you take a random step of length 1 in any direction at each point. But in that case, you'll go through the origin with probability 0, so it doesn't matter.
Just is conformal invariance of the random walk of any use in this problem?
Yeah. So that's how they proved the all the results with Brownian motion. You use the conformal invariance. Yeah. And then the result of Belizal was by relating random walks to Brownian motion. Okay. Okay, and so then finally, the arguably more physical model is where you say, well, if you're winding around the rod, then you can't pass through the rod. So let's condition the walk to not pass through the rod. And so then, in that case, we again have the same log. Should use the mouse. So again, the same rescaling, but a different limit value. And so the reason, intuitively, the reason is that if you take when you condition to not pass through the rod, that forces the walk to be somewhat far away from the rod in general. And so the claim is that the behavior of our models is the same as this last case, because we're going to force the walks not to pass through the origin.
So the Belizal result,
Yeah.
they did not force the walk to pass. So what is the difference between?
Yeah. So in most of the models that I have, I can draw. Okay, I can see. So if we have a lattice, so basically I say choose a point, well, the origin, and say we can't pass through there, and then consider the winding angle around this point. So what Belizal did was considering walks either by winding angle around some point that isn't on the lattice anyway, so then the walk isn't affected, the walk itself isn't affected by the fact that you're considering winding. Yeah, well, that's the difference between the results. And so, okay, so some of my results consider also points that you can't pass through, and then you get the same results as Belizal, but I'm not going to talk as much about that. Okay. Okay, so just to give precisely what the model is. So we choose some step set, which is this is basically any set of nearest neighbor steps, so that is nearest neighbor and diagonal. So for example, this could be the step set. And we want to now determine the number of walks from 0, 0 of each length each endpoint and winding angle. Okay, so we have now 4 variables, one for the x-coordinate, one for the y-coordinate, one for the length, and one for the winding angle. Okay, so this a priori is a bit inconvenient because theta is a real number and not an integer, but or equivalently we can think of walks on this, spiral thing. Okay, but yeah, so to get rid of the dependence, to get rid of the fact that theta is a real number, we consider this generating function, which is a sum over these, again, x to the I, y to the j, t to the n. But now we're just taking the floor function of theta divided by 2 pi as the power of s. Okay, and so basically what that means is that we don't need to consider the exact value of theta. So basically the factor of s will multiply by, the power of s will increase by 1 when we go up through this dotted line, and decrease by 1 when we go down through this dotted line, because that's when theta will move between being equal to or multiple of 2 pi or just. Okay, and so this, we actually don't lose any information by doing this, because the exact value of theta can be recovered from this sort of integer value by adding the argument of x and of the final endpoint, because we still have the information of the endpoint.
So wouldn't it be a bit simpler to just integrate over theta, and then you don't even need x and y anymore?
I don't know. I mean, this is a problem we can solve. So, wait. So we want the information of the endpoint as well. So this way, we're solving for something that has the information of the endpoint and the winding angle. But yeah, that would be interesting if there are ways that simplify this. But anyway, this model has all the information, so we're going to work with that. Yeah. Okay. So just as a preview, to sort of give an idea of the kinds of results we get. So if we choose this step set, so this is called the double Crevaras step set. If we just count excursions, so that is walks starting and ending at the red point, we get the following results. So the results are all in terms of this power series. So this is a power series in Q and U, defined here. And okay, so the form of the results take is that we have, first of all, Q is a series in T, defined by this equation, in this case. And so to understand this, the left-hand side here is a power series in Q, because this is a series in its variables. And the right-hand side is the power series in T. And so there's a unique series Q, which makes these equal. Okay, and so then now that Q is a series in T, this whole expression is a series in T and S, and it's precisely the expression which gives excursions, which gives the series for excursions with the double Crevaras lattice from 1, 0 to 1, 0. Again, as always with T, counting the length, and S counting the winding angle. Yeah, and so this is written so in a way where you can understand it as formal power series, which is nice from a combinatorial perspective. Alternatively, this can all be written in terms of the theta function. So the Jacobi theta function is this well-known function which is related to, which is defined like this, and which is related to, simply related to t. And okay, so we can write everything in terms of the Jacobi theta function. That makes it a little bit less obvious how it expands as a series, but it will be useful for getting asymptotics, and it's also, this is how we solve the problem. We really solve it by using complex analysis and theta functions. And then afterwards we can kind of use the series to expand things exactly. Okay, so on to the next part where I'll talk about how we derive functional equations for this model. So yeah, feel free to ask questions at any point. Yep.
Actually, the emergence of a theta function seems to indicate that there's some surface of genus 1 somewhere in this problem.
Yep.
Is there an intuitive way of understanding that?
Yeah, so I'll get to that in part 3.
Since we are in the intuitive way, the log t, I mean, can you just, I mean, I don't remember why it's log.
The log.
Yeah, why is it log t? I mean, is it obvious intuitively?
No, not to me.
Exponential theta. Okay.
Right. So the question is why? Yeah. Well, indeed, this is a good question. I mean, I can see intuitively why it's always the same. Like if it's log t for one version, it should be log t for the others. Yeah. Okay. But yeah, anyway, the explanation for the surface of genus 1 is very simple, but it's later in the talk, so yeah. Okay, so
the lattice doesn't actually really have a meaning. Only the points of the, I mean, not the edges of the lattice are not really.
Yeah.
Because you can skip them, right? You're allowed to.
Yeah. So I maybe should not talk about that. Sorry.
Is it angular lattice? No. You also have those. Oh, your diagonals.
Yeah. So in this case, we're allowing this step set.
Okay.
Yeah. So
in the previous result, for instance, we saw that these s's first appeared for t to the 6, which is because in this case you're allowed to cut through. You're actually allowed to walk kind of inside the little thing.
Yeah. So for the previous result, it was a triangular lattice. Okay, I can just go back to that. So we had this thing, and so with the diagonals in, and then you can see that the shortest path that will have an S sort of goes like this.
Yeah. So you're allowed to cut the corners.
Yeah. Yep. Yeah. So there's no good reason why I drew it as a lattice, maybe. But I guess it was just to emphasize that you're not allowed to go to this point. Okay. Okay, so for this section we're deriving functional equations. So it's a little bit more complicated than the functional equations we derived for walks not counted by winding angle. And so to write functional equations, we need to introduce a few other series. So first of all is the series T, which counts terminating walks. So that is walks that just end at the blue point, so where we allow them to go to the blue point, but only at the end. We're going to have R, which is rising walks. That's walks whose last step passes up through this purple dotted line, where we have the factor of S. And then sinking walks, which is walks whose final step goes down through this line. Okay, and so to write functional equations, as before, we have, so if we don't consider the winding factor, we get an equation that looks similar to before. So we have a walk is either an empty walk, which now has value x because it starts at 1, 0, or it's a walk with an extra step on the end. Okay, so now pxy is a Laurent polynomial which takes the which has the information of the step set inside it. I should describe this clearly if I'm going to answer the question about why there's a genus 1 surface. So just as an example, if we take our so if we take the step set this step set from before. Then P x y will be xy coming from the upright step plus y from the up step plus 1 on x from the left step plus x on y from the down right step. So it's basically the weight you get, the sum of the weights from the steps. And so then multiplying by t pxy is exactly just adding a step. Okay. So we have that a walk is either a walk with no steps or a walk with a step added at the end, except that a walk with a step added at the end could also be a terminating walk, which isn't counted as a walk. For the walks we're counting with W, you're not allowed to go to the you're not allowed to go to 0, 0. Okay, so that gives us this equation if we're not worrying about the winding method. But now we need to correct for the fact that we want to multiply by s when we pass through that dotted line that I mentioned. And so the correction is that, well, in W we really have the functions r and s, because rising walks and sinking walks are walks counted by W. But if in the walks with a step added, there's something where the multiplication by s hasn't happened, or by either s or s inverse hasn't happened, and so we need the 1 on s here and s here to correct for that. So anyway, we get this functional equation relating W to T, R, and S. And then this functional equation, along with some sort of fairly simple relations between RS and W, uniquely define the series involved. Okay, but so this is a sort of first functional equation that we consider. But before we analyze this, we're going to describe a refined functional equation.
Sorry.
Yep.
Can you explain a bit slowly how you take care of the fact that there are no, like you separate the origin?
Sure, I can describe that. So in W, so essentially the only difference between W and the only thing we have to correct for is when we multiply by this S. So if we consider the problem of counting rising walks, W, X, Y, well, really there's still the variables T and S in there, but they didn't fit. So W, X, Y, T, S. Let's say in this rising walks are counted by X, with also the variables T and S, but I ran out of space. So in here, rising walks are just counted by Rx because that's the definition. This is just counting walks. Whereas in the other, in W times D times PXY, so this is walks plus a step. In here, rising walks are counted by Rx over S. The reason being that we should have multiplied for when we pass through this line, we multiply by s, right? So the problem with here is when we added the last step, we didn't multiply by s, right? And so that means the factor from rising walks in here is actually Rx over S, because we forgot to multiply by S. And then the same sort of thing happens with S in the... Okay, so to correct for the difference in rising walks, we need to subtract Rx from here and then add Rx over S to get the thing that's in here. And then similarly for S, we do the same thing except that, well, when we go down, we divide by the factor of S, and so it's like 1 over 1 over S.
So I was asking,
Yeah.
like the origin,
Yeah.
how do you account for the fact that your walks are not allowed to take steps from the origin? So you separate out the terminating walks in some way,
Yeah.
but like how do you account for the fact that like none of your walks will have steps starting from 0, 0?
So the starting point is 1, 0, and so the thing that, so it's just t. Terminating, this factor comes in because the walks aren't allowed to go to 0, 0. And
so on your left hand side,
yep.
There are no walks which take steps from the origin.
No. I see. No, because W is only counting walks that don't go to the origin, that don't touch the origin. So walks that might touch the origin are counted by this plus this. Good. So yeah, that's. So hopefully it's completely explained now where these functional equations come from. So yeah, for the refinement, we cut W into 4 pieces. So yeah, what we do is we so we break W, which counts walks ending anywhere in any of these 4 quadrants. We break this into Q0, Q1, Q2, and Q3. So where Q0 counts walks ending in this quadrant, which I call Q0, but in a different one. Q1 counts walks ending in this quadrant, Q2 counts those ending in this quadrant, and Q3 those ending in this quadrant. Okay, and so then, somewhat trivially, W is equal to the sum of these 4 generating functions, because every walk finishes in one of these quadrants. Okay, and so now, just by looking at walks from that end in Q0, we can write a similar functional equation to before. It's just now, so now we have a correction for walks and moving out of and back into this line, Q0 by this side, and similarly we need a new correction terms for moving in and out of this line. So I'm not going to describe that in detail, but it's using the same ideas we get this functional equation. Okay, and so to simplify that, we can write these functions f, which f stands for either flow or flux. I'll just say flux. So we let f0 be the sort of like the flux over this line, so that is the generating function for walks entering minus those exiting over this line, and then f1 is the flux over this line. So somehow the solution is going to involve something that looks a bit like Gauss's law of magnetism, that once we cancel out some terms, the flux over one border is going to be the same as the flux over the other border. Right, and so we're going to do the same, so we'll have an F2, which is the flux over here, and F3, which is the flux over here, then F4, which is also the flux over here, but from a different perspective. And we get very similar looking equations. So we get this system of equations, and then F4 is related to F0 because they're both considering flux over the same line, but for F0 it's more from the perspective of the upper right quadrant, and for F4 it's from the perspective of the lower right quadrant. Anyway, so the factor of S comes in because of moving over that line. Yeah, and so this is our system of equations. We can slightly simplify it by writing the kernel as the factor of, as 1 minus t p, so to collect the factors of q, which is sort of the most complicated bit. And so then we just need to solve these equations. Okay, so the first of these being for the 4 different values of j, this is all 4 of these equations. Okay, so I'll go quickly. Okay, so for the next part, I'll describe how we solve these functional equations briefly. Okay, so the idea comes from work that people did on counting walks in the quarter plane. So the idea is we fix t to be small enough that these series actually converge, so we can really think of them as functions. At least they converge for certain values of x and y. And then we're going to look at the region on which the kernel is 0. Okay, so then if the kernel is 0, that cancels out the factor of q, and we get this equation. Okay. And yeah, so this is where I can finally answer this question about the surface of genus 1. So the surface of genus 1 comes up because this curve on which the kernel is 0 is almost always a surface of genus 1. At least it's a surface of genus 1 in all the interesting cases that I'm considering. And so the reason for that is that it's just the 0 set of essentially a quadratic equation. I wrote it up. Oh, it doesn't. No, I wrote it. Oh well. Because yeah, so the kernel came from this 1 is pxy, and pxy was the Laurent polynomial counting the steps. Okay, so yeah, that's where we get our surface of genus 1. Okay, so I should go over this quickly, but so we can since it's a surface of genus 1, we can parameterize it with functions satisfying equations like this. So I'm not going to go into, I'll skip the bits where I talk about more information about x and y. Just that the important thing is to know that x and z and y and z parameterize this curve on which the kernel is 0. And now if we skip all this stuff, then yeah, so we can, so recall that we were trying to solve these equations. And yeah, to do this we can write f, we can define sort of flux functions of z. So z being the variable that x and y are written in terms of. And okay, so this stuff on the right is just to do with, to make it so that the series converge nicely. So as long as they do converge nicely, we get equations that look like this. And so, so yeah, here it's looking more like what I was talking about with Gauss's law, where the flux, we almost, this equation is almost saying that the flux over one line is equal to the flux over the other line. It's like this bit is sort of like a charge that comes from the starting point of the walk. T is actually included in the flux because that's the that's counting walks that exit into the point, the origin. Okay, so we get this equation for each j. And so now just adding this up over all the values of j, we get an equation relating f of 0 to f of 4. So the weird thing that happened with the convergence and this choosing spaces where the things converge meant that somehow f of 0 is equal to s. Essentially, there's a shift. So there was already a factor of s between f of 0 and f of 4 in the functional equations. But now, because of the convergence thing, there's this shift between the input of f of 0 and f of 4. Because somehow, when we were considering the equations relating to flux, we had to consider them on different parts of the curve. And anyway, in the end, there's this shift. So we need to solve this equation, which simplifies to just an equation for f of 0. The sort of complex analytic equation, which is, but it's a relatively simple looking equation now. And in fact, it looks very similar to something satisfied. Oh, sorry, okay. Well, let's skip over this a bit. And right, sorry. Okay, so if we write s as this factor, so we define kappa so that s is something like this, then we need to solve an equation, and then we write a as something to do with f, then we just need to solve an equation that looks like this, with a bit of extra information that comes from complex analysis. And we can solve that exactly in terms of theta functions. So essentially, this equation is satisfied by both this bit and this bit, and the sum of them, and this factor here are just to deal with details about stuff we can prove about the poles of these functions using the functional equations. Okay, so, all right, and so I skipped over the bit where I defined x, but all of these variables, so alpha, beta, delta, and everything involved in the definition of x. Okay, so there's this parameterization of the kernel curve, which is well known from work of people counting walks in the quarter plane, and it involves a function x of z that looks like this. And so then in terms of all these variables, and also variables used for the y of z function, we have this exact solution for a of z, which is related to the flux. And
so a is a function defined in a strip with some periodic condition.
Oh yeah. So a. Right. So a is defined. So it's defined, yeah, on a strip, but really all of these extend to meromorphic functions on all of C. But yeah, sorry. So yeah, so it's defined by the series on the strip by substituting in x of z.
It has some pole structure, but I don't understand.
Yeah. So the pole, so really the statement about the poles is just saying that it doesn't have any poles where it's well defined, because we can prove that the series converge, and then it's related to other. So in the functional equations, it's a bit complicated, but whatever. So these functions of z, we can prove that none of them have poles in the regions where they're defined. And then, so the relation between them tell you essentially that they don't have many poles, and that's what we use to uniquely define them along with this equation. Okay. Okay, so anyway, we get this this exact solution for this thing A of z, which was related to various things including the generating function at the start, and we can essentially move back to so from A, now that we have this exact expression for A of Z, that gives us an exact expression for F0, which was the flux over a line, which gives us exact expressions for R and S, which were sort of rising and falling walks, the series for rising and falling walks that I described before. And then the full generating function is in terms of them. So in the end, it's a fairly complicated expression, but it's exact. So that's it.
So it's quasi-periodic in the pi tau direction. It doesn't have good quasi-periodicity properties in the pi. In the other period.
Yeah, sorry. So everything here is periodic in pi.
Okay. So you can also write it. Okay.
Yeah. So just from the definitions at the start. Yeah. So they could be written as everything being a function of on C quotiented by pi z. Okay. All right. So we moved back to this, but okay. So I mean, I haven't really been able to, or I haven't written out the full expression for W by doing all this backtracking, but for excursions, we can write out the expression exactly. So if we just count walks starting and ending at 1, 0, then we get this exact expression. Yeah, okay. So that's good. So now for the this final part, we'll just describe some special cases where the solution looks relatively nice. Okay, so I'll just show some special cases. So for simple walks, so if we have this step set, then in this case the kernel is parameterized by expressions looking like this, where gamma is just pi tau over 4. So in other words, for simple walks we have this parameterization with just one variable which is related to t, is tau, and so that's determined by this equation. And so Q is this series in P. And then for this case, we get this expression for excursions. And so this was previously found by part, or a slightly different expression, but equivalent. Okay, so yeah, so in this case, it's slightly nicer because we only have one variable. There are a few other cases like where we get the same thing. So for diagonal walks, we have these expressions. For reverse parabolas walks, we have these expressions. And for double parabolas walks, we have these expressions. Okay, so just going back to simple walks, I wanted to describe a bit about the asymptotic results we get from all this. So yeah, this is the expressions again for excursions. Right, so in this case we can also get explicit results for unrestricted walks. It was too big to fit on the page in this font, so in a slightly smaller font, here's the expression for unrestricted walks. So that is where we don't care about the endpoint, but we still care about the amount of winding that happens. Okay, so those were exact results, and we can also get back sort of these results about the limiting distribution of the winding angle. So we have exact solutions, so we should be able to extract all that stuff. And we can. So yeah, if we just consider excursions, so walks starting and ending at 1, 0, then we have again the log n factor, but we now have this slightly different limiting distribution. And then for unrestricted walks, this is the claim that I said at the start, which is that we get the same behavior as for Brownian motion avoiding some disk. And so this was also noticed by Bud in his work. Okay, so we get exact results for the density of the limiting distribution for winding angle for both excursions and unrestricted walks. Okay, so this was just a bonus part that I didn't think I would have time for, and indeed I don't. So finally, further problems. So walks by. So yeah, there are a few other problems we could ask. So, what about if we add in larger steps? Because all of this was only considering walks where the steps could only be nearest neighbor or diagonal. But this becomes harder because the curve is no longer genus 1, now has higher genus. Maybe walks going around multiple points would be interesting. I'm not exactly sure what a good model to study exactly for that is. And then, yeah, there are lots of other problems that come from physics that are maybe too hard, but worth thinking about. Okay, so thank you.
Other questions? Maybe I have one. So in your last result about asymptotics, so you said that for unconstrained walks, you have the same law as for Brownian motion avoiding a disk. But is there a discrete model for which you have the other law for the?
Yes. So actually, even in my result, I just didn't write it. So if we take diagonal walks, and this is something Tim did as well, then the fact that the walk couldn't go through the origin anyway means that we'll get the same limiting distribution as the Belisle result, where oh wait, so maybe this wasn't the question, but anyway, so we get the result for winding where it's not conditions to avoid point because there's really no condition. Although I guess there's another question there too about whether we could extract somehow the Spitzer result.
But the difference is really that it boils down whether the discrete wall can hit the forbidden point or not.
Yeah. Exactly.
If you count the winding around the point which is not on the lattice, does the result changes? Do you have?
Yeah. So it's exactly if you count. Oh, sorry. No. So the result, the limiting result is the same whether or not the point you wind around is on the lattice, except that essentially the result is changed by the fact that it's forbidden to go through this point. So like
if you count windings around the point which is not on the lattice, then you can you are free to not to restrict. So does this?
So then you get the same result as that is the Belisle result, where it's really a random walk and not a conditioned random walk. I say you get the Belisle result. That is exactly the Belisle result.
Thank you again.